In this video, we're going to practice using the first of the two algebraic solution techniques for solving exponential equations using logarithms. So the first of these methods is employing a logarithm of any base that we want in order to solve these equations. And so the first step is to isolate the exponential part of this expression, so whatever the base to the exponent is. So the first thing we need to do is divide by 6. So we'll end up with 7.2 to the x equals whatever 525 divided by 6 is. You can use a calculator if you want to get that. I'm just going to go ahead and leave it in exactly that form. So now we are going to rewrite this in logarithmic form. So we have a base, we have an exponent, we have the result of that process. So when we rewrite this as a log, this is equivalent to the log base 7.2 of our result, 525 divided by 6, to give us the exponent. So whatever the value of this expression is the value of x that makes the original equation true. Now this is perfectly fine if you have a graphing utility or a calculator or anything that can allow you to evaluate expressions, logarithmic expressions of any base. Now not every calculator can do this, so we're going to have a second example, a different way to solve these equations if you don't have a way to calculate that. But a lot of modern calculators have the ability to do logs in any base. You can also always bring up utilities like Desmos will allow you to evaluate these expressions as well. So we can type in log base 7.2 of 525 divided by 6. And we actually get an answer here. We get approximately 2.2652. So this is the value of x approximately that's going to solve our original equation. Now if we come back to Desmos one more time here, we can also verify our solution by graphing. We can graph the original function, y equals 6 times 7.2 to the x. Right, so we graph that function, and we're then going to graph y equals 525. We're going to see where the value of 6 times 7.2 to the x equals 525. So we just need to get 525 on the y-axis visible, find that intersection point, and it verifies. We get to about 2.265 as our solution. Let's look at one slightly more complicated example just to show you that the basic concept is the same. Again, what we need to first start off by doing is isolating that exponential part, so that base to some exponent. So we need to figure out what its value is. So 10 times the value of that plus 5 gives us 6. So the first thing we do is subtract 5, so we can figure out what the value of just 10 times 3 to the x plus 4 gives us. So that's going to be 1. Right? Subtract 5 from 6. So then we divide by 10 to isolate just the value of 3 to the x plus 4. And so that'll be 1/10. So now we rewrite it in logarithmic form. So the base is 3, so we're looking at an expression, a log base 3, of the result of the process is whatever the value of the exponent is, and the exponent in this case is the expression x plus 4. So then the value of x will be whatever the log base 3 of 1/10 is, minus 4. So this would be the exact form of that answer. Again, you can always use a calculator and figure out the decimal approximation, or if you're working in the iMath AS program, you can just type this expression in and it will show you what its approximate decimal value is.